Good morning, everybody. My name is Ferdinand Gerhardes. I'm from Anritsu, Engineering and Technology Group of EMEA. Here today we would like to give you a short introduction what means material measurements in the millimeter band, namely in the E-band. Similar setup as previously we discussed the antenna setup. I would like to give you first of all the reason why we are doing this. Imagine you have a car radar and the car radar is behind the chassis of your car and the electromagnetic wave is going through the chassis and you need to know what kind of deviations will the electromagnetic wave have when she is passing through. In other words, you have to characterize what kind of material is it. You would like to know what is the permittivity, you would like to know what is the permeability of such a material. And this can be done using one of these novel E-band VNAs, where we have here more or less a VNA, where we have here a new novel antenna architecture doing this. And here in the middle, we will have a fixture for the so-called material under test. The whole setup was developed by three parties. That's first of all University Aachen of Germany, that's the Fraunhofer Fundamental Research of Germany, and that was on the other side Anritsu that is supporting this idea. And now it's time to hand over to my colleague, Mr. Culotta from University Aachen, that is giving you a detailed insight how it's done.
I'm Cosme Culotta-Lopez from the RWTH Aachen University in Germany. And as Mr. Gerhardes already introduced, it is a work cooperation between us, Fraunhofer, and Anritsu. So the setup looks like this. Here we have two very directive antennas that were manufactured by Fraunhofer FIJR. The antennas are dielectric drop antennas designed by Professor Paul in Bochum. The concept is that this dielectric drop models the beam and shapes it to be very directive. The beam has a spot of around 28 millimeters, which ensures that the transmission is almost complete with no losses in the middle, except for the loss in the dielectric that we will calibrate out. So to ensure that the measurement is going well, we have to calibrate the setup before. The principle of the measurement is a transmission measurement with a probe in the middle. Through the characteristics of the probe of diffraction and transmission, so the 4S parameters, we can calculate the dielectric characteristics out. We start with the calibration, and the cal kit is probably one of the cheapest of the history, with just a metal plate. This metal plate will model our short and our match characteristic. I'm going to show you how. This is just a short. So we have two reference planes, one here and one here. So this is the short for plane 1. I'm clicking it in our graphical interface and already calibrated. Then I just rotate it, so we match it to the second reference plane for the second antenna. And this is short too. As you see, I'm not taking a lot of care to align it well or not, because this method is actually very robust. The precision, yeah, it will be a little bit worse in this trial, but it will be much quicker and much easier to see. Now for the match, I applied a little trick. If we rotate this plate 45 degrees, we're actually emulating the behavior of a match. Why? A match is nothing else than ensuring that the whole power is being delivered. Well, that means that the antenna doesn't have to receive any power back. Since the antenna is very directive, I'm directing all the power to me, because I absorb the power much better than an analyzer, I think. And this will emulate a match. So this is the load 2. Then I rotate it the other way around to simulate the load for the first antenna. And I direct it to me again. Then I press again to load 1. And now I just need to put the through standard in and start the measurement. And we've changed it, and now here's the sample holder. It's very important that both plates of the sample holder have a distance that is the same as the thickness of the probe we're going to measure. If we want to measure probes with all this thickness, that's not a problem. We change the distance between both plates of the sample holder and we calibrate again. The calibration, as you've seen, is really quick. Now we can measure the through standard like this and save the calibration. And it's all done, all set. Now we can introduce the probe they want to measure, in this case PTFE, Teflon. 8 millimeter thick. And clicking on measure, so we have the sample here in the interface, we put the name, Teflon, the thickness that must be known, 8 millimeters, and the value that we expect it to have. This is a starting point for the iterative algorithm that we're applying afterwards. So Teflon is a very well-known material because the dielectric constant stays almost at 2.1 for all the frequency range up to a very, very, very high frequency. Of course, at 77 gigahertz, it will sink a little bit, but it will still be very close to 2.1. So I just write 2.1 as starting point. Then I press measure, and the measurement is ready, already. So before applying the algorithm to calculate epsilon, I will apply some time gating to avoid and filter out the multiple reflections that are taking place after I introduce this sample, apart from the direct path. So I apply a rectangular window with a width of 1 nanosecond. And now I calculate the constant. And here you have it. If you can please zoom the screen, you will appreciate that here in the sides we have some kind of artifacts that are a product of the filtering, of the windowing. But the constant stays very close to what expected, so close to 2. And this little wave that you can see is a little measurement inaccuracy that we can't correct out right now because it's due to the probe itself introducing a phase delay, so introducing a standing wave that's very close to the direct path. But what is that? 0.02? Thank you very much.